It's just a quick review video for Chapter 3 Exponential Functions. So this would be a good video to watch before you write your unit test for this chapter. I'm just going to do a few questions that you can find in the review I posted on jensenmath.ca. So we're going to go through each section that was covered in this chapter and just do an example of a question from each section. Before I do that, just a quick reminder of the general equation of an exponential function that we're going to be working with, or that we worked with for this chapter. The equation is y equals a times b to the x, where a is our initial amount, that's what we start with, b is our growth factor or our decay factor. So it's a growth factor if b is a value greater than 1. It's a decay factor if b is a fraction between 0 and 1. Y represents our future amount after our initial value has been repeatedly multiplied by our b value. And x is the number of times, so our exponent of x. Notice the exponent, our variable is in the exponent for an exponential function. The variable of x represents the number of times a is going to have been increased or decreased by our growth or decay factor. And to figure out the value of x, don't forget that you have to do total time divided by time it takes for one growth or decay period. So future value, initial value, growth or decay factor, growth if it's bigger than 1, decay if it's between 0 and 1, and x represents the number of times that our initial value is going to be multiplied by our growth or decay factor. And you calculate x by total time divided by time it takes for one growth period. So we'll start with exponential growth. So what we have here, our bacteria culture doubles every 15 minutes. So first of all, notice that it's doubling. So that's exponential growth. So our growth factor, it's going to be repeatedly doubled. So our initial value is going to be repeatedly multiplied by 2. It's going to be multiplied by 2 once every 15 minutes. Okay? So keep in mind here that the number of times it's going to be doubled, so that'll be our x value, is going to be our total time divided by 15, because it gets doubled once every 15 minutes. Because remember, don't forget, for x you always have to do total time divided by time it takes for one growth or decay period. It takes 15 minutes for one growth period, so we have to do total time divided by 15. And there were 20 individuals initially, so we started off with an initial population of 20. How many bacteria will be present after 2 hours? So first of all, we need to keep our units consistent. Since our growth factor was given in minutes, we should convert our hours to minutes here. So keep in mind 2 hours is 120 minutes, so I'll change it to 120 minutes. So how many bacteria will be present after 2 hours? Let's figure out everything we need to know here. We're looking for a future value, so we're looking for y. Actually, I'll write the general equation first. Y equals a times b to the x. We're looking for the future value after 2 hours, or 120 minutes. Our initial value, a, was 20. Our growth factor, our b value, is 2. And x is the number of times it's going to be doubled. So how many times will it double in 120 minutes? If it doubles once every 15 minutes. Well, to calculate x, total time divided by 15, so we have to do our total time, 120, divided by 15. And 120 divided by 15, well, that's 8, so I really need to do 20 times 2 to the exponent of, 8. 20 times 2 to the exponent of 8. What does this equation mean? This means that our initial value of 20 is going to be doubled 8 times. 2 to the exponent of 8 means 2 times 2 times 2, so on. It means 8 factors of 2 being multiplied together. So if we were to multiply this out, 20 times 2 to the 8, I'll show you on the calculator for this one, just so you know where the to the exponent of button is on your calculator. So on your calculator, make sure you know how to type this in. 20 times 2. Make sure you know where your to the exponent of button is. On this calculator, it's that button right there, to the exponent of 8. So it'll do 2 to the exponent of 8 first, and then multiply it by 20. If we evaluate that, we get 5,120. So y equals 5,120. And then you should write a nice concluding statement that says there will be 5,120 bacteria present after 2 hours. Let's do another question. This one's a continuation of our first question, where we're actually going to be solving for time. So we're going to be solving for something in the exponent this time. How long will it take to grow a population of 163,840? So this time it gives us our future value. It gives us y. So keep in mind our general equation is y equals a times b to the x. And don't forget, I'm going to make a note on the side here, don't forget x, we always have to do total time divided by the time it takes for one growth period, which was 15 minutes in this scenario. So let's not forget that. So after we solve for x, we're going to have to take into account this equation to figure out the actual total time it's going to take. Solving for x will just tell us how many times their initial value has to be doubled in order to get to 163,840. So if we remember back from the beginning of our question, our initial value was 20 and our growth factor is 2. So we can plug in everything we know into this equation. We know, I'll do this in red. We know that our future value needs to be 163,840. We know our initial value, we started with a bacteria culture with a population of 20. It's going to be repeatedly doubled, but this time we're solving for x this time. We need to figure out how many times do we have to double 20 so that it gets to 163,840. That's what we're going to do. So this is the process you're going to go through to solve that. First thing you're going to do is you're going to isolate the power by dividing the 20 to the other side. So you're going to do 163,840, and you're going to divide that by 20. That way we isolate the power. So equals 2 to the x. If we do that division, we get 8,192 equals 2 to the x. Now, here's where you can either go through some trial and error process to figure out 2 to the exponent of what equals 8,192. If you don't want to go through trial and error, what you can actually do is use the power rule for logarithms, and I'll show you how we're going to do that. Oh, sorry, it's just lagging a bit for me here. I just need to wait for it to get back on track here. Okay, I'm going to zoom out a little bit. Okay, so what we're going to do is we're going to take the log of both sides. So I'm going to do log 8192 equals log 2 to the x. Now the power rule for logarithms tells me when I'm taking the log of a power, I can take the exponent of that power and move it in front of the logarithm. So what I can do is actually take this x, bring it out front of the log as a coefficient. So what I have now, I'll get some more room here, I have log 8192 equals x times log 2. Now I can isolate x by dividing the log to the other side. So I have log 8192 divided by log 2 equals x. And you can just type that on your calculator. On your calculator you should have a log button. In my case it's right here, so I do log 8192. Don't forget to close your bracket, divided by log 2, and we get x is equal to 13. So that tells us 2 to the 13 is equal to 8192. And we could just verify that quickly just to show you here. 2 to the exponent of 13 is 8192. So let's write our answer here. X equals 13. So what does that tell us? That tells us that our initial population of 20 has to be doubled 13 times. We solved x to be 13. Well, how long will it take for it to be doubled 13 times? That's where this, so we're not done the question yet, that's where this equation comes back into play. If it has to be doubled 13 times, but don't forget from earlier in the question, it only gets doubled once every 15 minutes. We're going to have to multiply our answer for x by 15 to figure out how long it's actually going to take for it to double 13 times. So let's plug, now that we know x, let's plug that back into our equation here. And we have 13, it's going to have to double 13 times, t divided by 15, and then solve by total time by just multiplying that 15 to the other side. And we actually calculate our total time to be 195 minutes. Time equals 195. So you'd write a nice sentence, it'll take 195 minutes for the population to grow to 163,840. Okay, let's do another example. This is another example of exponential growth, but this time it's going to be given to us as a percent, the growth, okay? So the population of a developing city increases by 8% per year. In 2005, 125,000 people lived in the city. What is the population expected in 2020? So we have our initial value. In 2005, it started off with 125,000. The population of a developing city increases by 8% per year. That's our rate of increase. I'll call that R. And what is the population in 2020? So that's 15 years away from 2005, so I'll just write 15 years here. That's our number of years. That's our x value in this case, if you want to think of it that way. So what we're going to do, we're going to use the same type of equation, except this time, the equation we're going to use is going to look like this. Y is our future value, A is our initial value, but instead of putting B here, since we're given the growth as a rate, as a percent, what we're going to do, I'm going to, in brackets here, 1 plus R. If it was decreasing by 8% per year, we'd have to do 1 minus R. But since it's increasing, that tells us that we need to do 1 plus R. Okay? To the exponent of x, the number of times it's going to increase by 8%. So we're looking for the future value. Our initial value starts off with a population of 125,000 people in the city. It's going to increase by 8% per year. Don't forget, we're going to write 8% as a decimal, so 0.08. And to the exponent of x, it increases every year. So in 15 years, it's going to increase by 8% 15 times. Now we just have to solve this equation. So what we're going to do is just type this on our calculator, 125,000 times 1.08 to the exponent of 15. If you want, I'll show you just the one more step of adding inside the brackets there. 1.08 to the 15. And if we evaluate that expression, I trust that you can do that. We get 396,521.1. So the population will roughly be 396,521 in the year 2020. So you should write a nice concluding statement that says that. Next, we're going to move on to exponential decay. I'll go through this a little bit quicker than I went through. I think I'm just going to do one example, two, okay. But I'm going to go through this a little bit quicker than I went through the previous example. And notice that these question numbers correspond to the questions in the review package on jensenmath.ca. So, when you read a question and you see the word half-life, that tells you right off the bat it's an exponential decay question. And that means, a half-life means that the isotope that we start off with is going to be repeatedly cut in half. So our decay factor, so B this time is our decay factor instead of a growth factor because it's repeatedly being cut in half, our B value is a half. The half-life of carbon is approximately 6,000 years. That means once every 6,000 years, our initial value of carbon-14 is cut in half. So the number x, the number of times it's going to be cut in half, equals the total time divided by the time it takes for it to be cut in half once, which is 6,000 years. A fossil of carbon-14 weighed 100 grams, so it started off at 100 grams. That's our initial value. How much would it weigh after 18,000 years? So that's our total time. That's our t value. So let's plug everything we know into our equation. Y equals a times b to the x. We're looking for the future value. If we start off with 100 grams of carbon-14, it's cut in half repeatedly over a period of 18,000 years. So how many times is it cut in half over 18,000 years? If it's cut in half once every 6,000 years, well, we need to do 18,000, our total time, divided by the time it takes for one decay period, which is 6,000. So I need to do 18,000 divided by 6,000. So my equation is actually y equals 100 times a half. 18,000 divided by 6,000 is 3. So what I have here is y equals 100. I could simplify this. A half to the exponent of 3, well, that power of 3 applies to the numerator and the denominator. So 1 to the power of 3 is 1. 2 to the power of 3 is 8. So I'm really just dividing 100 by 8, or multiplying it by 1 over 8. So if I do that, I get 12.5. So after 18,000 years, the 100 grams of carbon that we started with is going to be down to 12.5 grams. So you'll write a nice sentence. It'll weigh 12.5 grams after 18,000 years. This question is going to be a little bit different. So a radioactive isotope decays rapidly with a half-life. So it's another half-life. So that tells us our decay factor is a half of 4 minutes. So it gets cut in half once every 4 minutes. So x, the number of times it gets cut in half, we have to take our total time and divide it by 4. For a 12-minute test, okay, so there's our total time, there's our t-value. So we're going to have to do 12 divided by 4 to figure out how many times it's going to be cut in half. Technicians need at least 6 grams of the isotope to remain at the end of the test. Okay, so it gives us our future value. It tells us how much we need to end with. That's our y. How much must they start with? So we're looking for the a value this time. So this question's a bit different. Let's write our general equation of an exponential relationship, y equals a times b to the exponent of x. We know why. We need, at the end of the 12-minute test, to have 6 grams of the isotope left. So we need 6 grams left. We don't know what we need to start with at the beginning of the test, but we know whatever we start with is going to be cut in half 3 times. Where am I getting 3 from? Total time divided by time it takes for one decay period. So 12 over 4. So my equation, 6 equals a times a half to the 3. Well, we had this exact power in the previous question. A half to the 3, we know that's 1 over 8. So we have 6 equals a times 1 over 8. Now we just need to isolate a by dividing 1 over 8 to the other side. So I have 6 divided by 1 over 8 equals a. Dividing by 1 over 8, that just means multiplying by 8. So this is really just 6 times 8 equals a. So my a value is 48. So you must start off with 48 grams of the isotope, so that at the end of the 12-minute test, you're left with 6 grams. Let's move on to transformations. I'm just going to do one quick example for transformations. We covered transformations in the previous unit, so this should be familiar to you. You should recognize this equation with the a, k, d, and c values. Those a, k, d, and c values are going to transform our parent function, and the parent function could be any number of different exponential functions, but what we're going to do is we're going to get key points for the parent function, then transform them based on the a, c, k, and d values. Don't forget a values will do vertical stretch or compression, and also a vertical reflection if it's negative. C values are going to shift it up or down. K values are going to cause horizontal stretches or compressions, and also a horizontal reflection if it's negative. And D values are going to do shifting right and left. Please notice that all the K and D are the horizontal transformations. A and C are vertical. K and D are in the exponent with the variable x. So anything in the exponent is going to cause a horizontal transformation. A and C are not in the exponent, so anything not in the exponent is going to cause a vertical transformation. Alright, let's do an example here. So we're going to, basically we're going to graph this transformed function using transformations of the parent function. So first of all, let's write the parent function. The parent function of this, disregarding the a, k, d, and c values, our parent function would just be y equals 2 to the x. And our transformed function is y equals 2, I can write that better, y equals 2 times 2 to the negative x minus 2, and then the plus 3 is not in the exponent, it's off at the end. So don't forget here, this is our a, this is our k, this is our d value, and this is our c value. So we'll look at how those affect the parent function after we write out some key points for the parent function. So let's write out key points for the parent function first. Always for, you get to pick your x values, and then we'll calculate the corresponding y values by plugging the x values into the equation. For exponential functions, it's easiest if you pick values between -2 and 2 for x. So -2, -1, 0, 1, 2. Let's plug each of these into y equals 2 to the x and get points, the y values for these points. So if I plug in -2 for x, 2 to the -2, well, that's 1 over 2 to the +2, which is 1 over 4, which I'll write as a decimal, 0.25. If I plug in -1 for x, I have 2 to the -1, which equals 1 over 2 to the +1. 1 over 2, well, that's just 0.5. 2 to the 0, anything to the exponent of 0 is 1. 2 to the 1 is just 2, and 2 to the power of 2 is 4. So there's my points for my parent function. Now I'll get some points for the transformed function. Let's look at the x values first. So let's look at what the k and the d values are going to do. Well, k is -1. That's going to cause a horizontal reflection. So I'm going to have to multiply my x values by -1. So I'm going to have to do -1x. And then my d value is 2. That's going to shift it to the right 2. So I'm going to have to add 2 to all of my x values. Next, let's look at what's going to happen to the y values. Let's look at a and c. Well, a is 2. That's going to cause a vertical stretch by 2. So I have to multiply my y's by 2. And I'm going to have to shift up 3. So I'm going to have to add 3 to my y values. So let's perform these operations to the points of the parent function, and we'll be able to graph the transformed function. So if we do that, you take each of the x values, multiply them by -1, and then add 2. So -1 times -2 is 2, plus 2 is 4. Now let me show you what happens to the corresponding y value for this point. The y value has to be multiplied by 2 and then add 3. 2 times 0.25 is 0.5, plus 3 is 3.5. So you'll just perform those operations for each pair of points, and I'll just write down what you'll get. 3, 4, 2, 5, 1, 7, 0, 11. So there's our points for our transform function. Now all you have to do is just plot those points. And also one other thing I want you to notice is we're going to have to decide whether the function is going to be increasing or decreasing after we graph it. That's another thing it says we have to state here. State whether each function is increasing or decreasing. So that just means as we go from the left to right, from 0 to 4, what's happening to the y values of the function? Are they getting bigger or are they getting smaller? So we'll state that after we graph it, but let's graph it first. Oh, one other thing I should remind you of. For exponential functions, there's always a horizontal asymptote at whatever the c value is. So since the c value is 3, I'm going to start by actually plotting a horizontal asymptote at y equals 3. And hopefully you remember, oh, I thought that was going to be a straight line. Here's the straight line function. Hopefully you remember an asymptote is an invisible line that the function is going to approach but never actually get to. And you'll see how that works as we graph the function. So there's my horizontal asymptote at the c value. It's at 3. So you start by always drawing your horizontal asymptote at whatever the c value is, and now plot your points. So there was a point at 4, 3.5, 4, 3.5, that's right here, 3, 4, 2, 5, 1, 7, and 0, 11. So, and then you'll just extend the pattern in either direction. As best as you can, make it a smooth curve, and notice that this function is going to get closer and closer to this horizontal asymptote, but it'll never touch it. It'll get closer and closer as we go to the right, but it'll never quite get there, and this will continue off to infinity as we go to the left. So now we should state that this function, as we go from the left to the right, this function is decreasing. The y values are getting smaller, so just label that this is a decreasing function. And also notice I put arrows on the end of my function to show that it continues in both directions. Okay, last section I'm just going to do quickly is just some properties of exponential functions, just so you understand what the graphs will look like. The a value is going to tell you where we're going to start. That's our initial value. Our a value is 5, so I don't know, I'll just plot it roughly right there. Our initial value is 5, and then our b value is 1/2, so that's a decay factor. So that means as we go from left to right, this 5 is going to repeatedly cut in half, so it's going to repeatedly go down. So the function is going to, I should make it curved a bit more. It's going to look roughly like this. That's roughly what the function will look like. Because keep in mind there's a c value of 0, so the horizontal asymptote is just at 0. This function, however, our initial value is -3, so it's going to start I don't know, let's say -3 is roughly right there. And that value of -3, as we go from left to right, is going to repeatedly multiply by 4. So at an x value of 1, that -3 needs to be multiplied by 4 once. So it will go down to -12. And as we go in, so it's going to be decreasing. So it's going to look something like this, and this direction. Keep in mind there's still an asymptote at y equals 0 because there's a c value of 0 off at the end here. So that's roughly what it's going to look like. That's just a good idea of how to just draw a rough sketch if you want to know what it's going to look like and be able to label whether, so this one's decreasing, right? Because it starts at 5, is repeatedly cut in half, and this one's also decreasing because it starts at -3, so it starts at a negative value and it's repeatedly multiplied by 4, so that negative value keeps becoming a bigger negative value. Lastly, the last thing you're going to need to know how to do is, given the graph of an exponential function, write the equation. So what you're going to do is just pick out some key points on the function. So when x is -2, so let me just make a quick little table of values here. When x is -2, y is 12. So -2, 12. When x is -1, y is 6. When x is 0, y is 3. And when x is 1, y looks like it's at about 1.5, and that would make the pattern continue properly. Notice that as we're going from left to right, as x's are increasing by 1, the y values are being cut in half, multiplied by a half, to get from one y value to the next value. They're repeatedly being cut in half. So that tells us that our b value, our decay factor, is a half, right? Because the function is repeatedly being cut in half, it's going to be a decreasing function. Also, this value right here, here's our a value. Our a value in this case is 3. It starts at 3, and as we go to the right, it gets cut in half, goes to a half, and so on. And our asymptote is at y equals 0, so it hasn't been shifted up or down at all. So we can write our equation just by plugging in our a and our b values into y equals a times b to the x. So you just pick out your y-intercept, that's your a value, so 3, and b, that's our decay factor, and which we discovered was a half, and then you leave your variable x, and there's the equation. So that's pretty much everything we covered for this chapter. I mean, we did some different variations of these types of questions, but this would be a good start for reviewing for a test. Make sure you go back through all your lessons and worksheets from the chapter and try out the practice test as well. So you can get all the materials from jensenmath.ca.